over to my partner in crime, Mike Scher here, who will introduce our speaker.
Thank you, John. So if I could remind everybody to mute or turn off your cell phones, that would be terrific. It's always nice to do an introduction for somebody who doesn't need an introduction. And Mike Adler has done, I want to say, at least 5 talks for us over the years, ranging from cosmology to geology and climate. And so, but nevertheless, I was asked to do an introduction, so I will.
I asked you.
Right. Mike graduated from MIT in '71 with a PhD in the area of solid-state physics. He worked at GE from '71 until he retired in 2000. He is very widely published in the area of semiconductor physics with over 100 papers, and based on this was a fellow of the IEEE, Institute of Electrical and Electronics Engineers, the largest technical society in the world. Mike has been active in that society for 30 years and was even the president of it in 2013. Mike has been pursuing his hobbies of astronomy and photography, and I urge all of you, before you leave, to go look over here for some incredible examples of Mike's photography. And I'm sure many of you have seen them around town, in the library, I think in the hospital, deep space objects. This is close stuff for Mike. On the astronomy front, in 2014, he built his own observatory at his house that houses a 20-inch, a 12.5-inch, and a 6-inch refractor. He had a 2-month exhibit of his photographs in the library, as well as other venues in town. He's been giving talks and will continue to give talks for us, including next month. So please join me in welcoming Mike Adler.
Well, thank you, Mike, for that very nice introduction. I'm a little embarrassed to give 2 talks in 30 days, but to be honest, this talk was supposed to be given a year ago, and if you remember, there was a snowstorm that wiped out, the whole town closed down. So, and then it got postponed to April, but then I gave this talk on Hawaii instead, and so this talk has been a while in coming. And so I'm a little backlogged on talks. But anyway, so here we are. We're going to talk about global warming, greenhouse, and, wrong direction. John reminded me. What we're going to talk about first is a little bit about the greenhouse effect. We're going to talk about some of the some simple models to help you understand that. Then we're going to go into measurement of the climate, and then some in comparison with some incredible models that have been developed over the last 30 years. Earth system models are called. And then we're going to do the projection ahead, which is always exciting. And also what it's going to take to make them happen, which is not going to be easy. All right, so the greenhouse effect. So here we have the sun sitting at 5,280 degrees Kelvin, and it emits light according to this it's called a black body curve. And this is the light that the sun emits. Here is the Earth. It's sitting at around 287 degrees Kelvin. And what happens is the sun irradiates the Earth, heats it up. The Earth then re-radiates in a much shorter wavelength. This is the actual curve for a body at 14C, or 287 K, and is this shape. And so it re-radiates, and what happens is the atmosphere reabsorbs some of this. And in fact, you can see it right here. The yellow areas, the red area is the only thing. This is measured actually at the top of our atmosphere. So the red area is the only thing that's actually getting out of the atmosphere. All this other stuff has been sent back to the surface of the Earth, further warming the Earth. And that's the greenhouse effect. What's happened is some of the radiation that comes from the Earth is essentially re-emitted back to the Earth. And what it amounts to is the Earth is losing less heat. It's not getting warmed by the clouds, it's just losing less heat, like a blanket. Okay, And just to give you a little perspective on this, there's been a very close correlation over the years of CO2 and methane, greenhouse gases, and the surface of the world. And this is thousands, this is 400,000 years before present. And you can see what's happened recently, by the way. But that correlation still exists. So this is not a new thing. I mean, that someone just uncovered. The CO2 and methane, these peaks line up very closely with the peaks in the temperature. And this is another set of data. All of this is from ice cores in Antarctica. Okay, so a little bit more about the greenhouse. So, but a little more, maybe a little more quantitatively. So here we have the sun emitting, and it turns out there's something called the Stefan-Boltzmann law, which goes like the fourth power of the temperature. But anyway, it tells by using that you can calculate what the actual emitted radiation from the sun is, and it's 6.2 times 10 to the 7 watts per meter squared. That impinges upon the Earth. And it turns out the way it works, the Earth absorbs it, but it only absorbs it according to its actual projected areas. Not the the way you work it out is by just projecting the area onto a plane like this, and that works out to be 342 watts per meter squared. So of all of this, this is how much is being absorbed by the Earth, or I should say, is being sent to the Earth. Okay. So now I'm going to show you some really simple models to illustrate what's going on. This model, the first model is to be one without any atmosphere. So forget that this absorbing layer there exists. It's not there. So what happens is the sun is irradiating the Earth. Some of it is reflected from the Earth's surface because the Earth is not a perfectly absorbing body, and that's called the albedo. It has 0.3, so 70% of the sun that hits the Earth gets absorbed. And if we're in an equilibrium situation, the Earth will irradiate just exactly the same amount. So what comes down when you take this 30% off is 237 watts per meter squared. The Earth will then re-radiate all of this, because if it doesn't, it's going to heat up. So we're assuming that we're in thermal equilibrium. It's going to radiate back exactly the same amount, keeping the temperature of the Earth safe. So you use this backwards, you go backwards on the Stefan-Boltzmann law, and guess what? You get a surface temperature of the Earth of minus 18 C. Now, isn't that nice? In other words, without an atmosphere, the Earth would not be inhabitable. Okay, it'd be around 0 F. I mean, it's, you can see that some form of life might exist, but probably not the form that exists here right now. Okay, so now we're going to talk about, well, what happens when we add an atmosphere. And so we're going to make this simple for the first illustration. The simple illustration is that we have a perfectly absorbing atmosphere. The atmosphere absorbs everything that the Earth is re-emitting. So just to go over this one more time, the sun is coming down. Oh, that's what I don't like about this pointer. The sun is coming down, and it's irradiating the Earth. The Earth now is going to irradiate that, but what's also happening is anything the Earth is irradiating back out is going to be absorbed by the atmosphere, because now we have an atmosphere. Half of that is going to be re-radiated back to the Earth. The other half is going to go out. And so when you add it all together, you get a temperature of 302 degrees Kelvin, or almost 30 degrees C, which is actually 85. And that's too high. That's not exactly what happens. But that's because we assumed a perfectly, where this layer absorbs everything. Well, it doesn't. Some of the heat from the surface goes right through the atmosphere and gets escaped. In fact, the right number is about 77% actually gets absorbed, and about 23% goes through. And if you plug in 77% of this, you get guess what? You get a temperature of 13 C, which is 55.4 F, which is exactly the average temperature of the Earth. But you can see that without the atmosphere, we would have a very difficult situation on it. So the greenhouse effect is not all bad. There's a very useful part of it, which is we're warming up the Earth to a habitable level. Okay, well, let me talk a little bit about some devil advocates. So some people say that can't be done. The Earth can't be heated by an object, the atmosphere, which is colder than it is. The atmosphere is up there, it's cooler than the Earth. So how can the Earth be warmed by the fact that we have an atmosphere which is colder than it? Okay, so you have to go through this in detail. So the first step is the sun is not warming the atmosphere. Most of that goes right through. It's warming the Earth. And the Earth is irradiating all the heat that is going up into the atmosphere is coming from the surface of the Earth. And it's radiating some of it back. And so what's happening is the atmosphere is acting like a blanket. And the Earth is just losing less heat. The atmosphere isn't exactly warming the Earth, it's just causing it to lose less heat. And that's what it does. This is analogous to you in your bedroom or whatever, putting a blanket on yourself, and the blanket it's not the blanket is warming you, you're just losing less heat. That's exactly what the atmosphere is doing. And for example, though, if you were, so if the Earth was not did not have the heat originally, if the Earth was not heated at all, the atmosphere would have no effect. Just like putting a blanket on a cold stove doesn't cause the stove to get warm. It's just keeping less heat from getting to state. And so, and then dealing with the subject of the temperature of the atmosphere. Think about what you just did today when you came into this auditorium. You were out in a temperature that was about 30 degrees, and you came into a room that's 70 degrees. Guess what? You felt warmer in this room than you did outside. You were able to take your coat off. Why? The room is actually lower than your body temperature. The room is at 70 degrees. Your body temperature is 98. So how can the room warm you up when it's colder than you are? The room didn't really warm you up. You're just losing less heat. Okay? All right. So anyway, the bottom line is the greenhouse effect is critical for life on Earth, but too much of a good thing can get us in trouble. To also put another dot on the I here about the greenhouse effect, a lot of measurements have been done to show that it's real. This one, this graph on the showing both of you. That's what I'm doing. This graph on this side shows the actual measurement of radiation at the surface of the Earth that is identified by these chemical species. You can see CO2 here and methane over here, ozone and various fluorocarbons over here. So the idea that the Earth is getting radiation from the atmosphere is not a myth. There's the data. It's getting radiation from the Earth, and that's the data. It's measured. It's not a calculation. Another interesting measurement that was done, and there's some recent papers on this that I've shared. There's another interesting measurement that's represented here. This compares the radiation at the top of the atmosphere. It's done through satellites between 1970 and 1996. And it shows that there's less radiation at the top of the atmosphere in these frequency ranges. One is CO2 and the other is methane. And what's happening to that is that's excess radiation that is now being absorbed on the surface of the Earth. And it's measured. There it is. It's just, there was more of that radiation in 1970 than there is now, because that excess radiation has been on the surface and we've warmed up because of it. And when you work out the numbers, that amount does result in about a 1 degree C increase in temperature from those dates. Okay. Yeah, so this is a more complicated model, and don't worry, I'm not going to try to explain it all. But I just wanted to indicate that there's a lot more going on than those simple models, and a heck of a lot more. This diagram tries to illustrate that. But the first difference is that not all the radiation from the sun goes right through the clouds. Some of it gets absorbed by the clouds. In this case, it was 67 watts. And then because of that, the clouds now have more heat, they absorb radiation from the surface, but they've also absorbed some of it from the sun, and they radiate more back to the surface of the Earth than it was in that simple model. And then on top of that, there are volcanoes and other sources of thermal radiation from the surface that weren't in that other model that also radiate upwards. But the bottom line is the answer is the same. Even when you work it all out, as it has to be, because the temperature of the surface of the Earth is 14 C. So the number from that simple model was 385 watts per meter squared. The number from the more complicated is virtually the same. So same result. Just the reason was the simple model was fudged to make it equal that number, but the more complicated model does validate it. Okay, so now we're going to move on to. We're going to move on to some planets. This is a little off the topic, but I thought you folks would be interested in this, and I got interested in it when I first were doing this. If you look at this chart, the top row here, let's take the second row first. The second row is the actual observed surface temperature of each of these, all the terrestrial planets: Mercury, Venus, Earth, and Mars. Now, the top row is the temperature that the planet would be with no atmosphere at all. And if you'll notice, Mercury and Mars agree very well. And it's very close. Earth doesn't agree, but I showed you that already. And even with a simple model, you can get an answer that's pretty close, it's very close to the actual with one simple one-layer model get you there, or the more complicated. But anyway, it's quite easy to get to the right answer for the Earth's temperature based on greenhouse effects that's occurring. But look at Venus. Venus is 735 degrees on the surface, and is way high. And even if you take, if you put in a single absorbing layer, you only get to 260. And if you assume everything goes through the atmosphere and the sun, nothing is reflected from Venus, which is a very bad assumption, it only gets up to 390 degrees. So why is Venus so hot? And one of the immediate thing is that the Venus's atmosphere is 100 times more dense than ours. So it's a very bad assumption to assume that all the radiation is getting through to the surface of the planet. In fact, it's a better assumption to assume that it's all absorbed at the top of the atmosphere. And if you do that and do that simple calculation, guess what? You do get a number that's very close to the measured number. You get a temperature of 210 K, and the actual measured temperature by the Magellan satellite, which was in orbit some years ago, you get 220 degrees. So it's very close. So it's a much better assumption for Venus to assume that all the radiation from the sun is absorbed at the very top. So the question still is, how can you get to the 730 degree temperature at the surface? And the answer is something called the runaway greenhouse effect, which unfortunately is going to happen on the Earth at some point too. But it happened to Venus because it's closer to the sun and it gets more radiation from the sun. So what's going on here is that you have the sun irradiating the planet, and it is causing, and Venus, by the way, when it first was formed, had a lot of water. Well, it's pretty clear it probably had almost as much water as Earth does. Water evaporates and goes into the atmosphere, and then it re-radiates based on the greenhouse effect back to the surface. But there's a little issue with a water-saturated atmosphere, and that there's a maximum radiation that can actually be emitted by the atmosphere, and it's only 30 watts per meter squared. So if the surface, if the radiation was compatible with that amount, it would be fine. But what happens is the sun continues to evaporate more and more water, gets into the atmosphere, more of its returned, but only the same amount can be radiated from the surface. So the planet just gets hotter and hotter and hotter until all the water disappears. It's evaporated. And so that's what happened to Venus some time ago, probably a long time ago, but it happened. And how do we know that, or is there any evidence that that happened? Yes. The hydrogen to deuterium, right? Deuterium is heavy hydrogen, And there's a ratio on Earth of that's 10,000, but on Venus it's only 100. Because what happened is all the light water, all the light hydrogen got swept away by the solar wind when the water on the surface was evaporated, and only left the heavy hydrogen left. So that's pretty clear evidence that Venus did have did lose the bulk of its water through this runaway greenhouse effect. And because of that, and the fact that Venus has no plate tectonics, there's no sequestration of the CO2, which is to first order probably about the same amount as we have on the Earth, resulted in an atmosphere that's 100 times more dense than on the Earth, and it's all made of CO2. But that still doesn't answer the question why it comes to 730 degrees. And this is really off topic, but I was so fascinated with it, I figured, how did this happen? And so I did a calculation on my own, and it turns out if you assume that Venus is most of the radiation, it's a closed body, and it doesn't lose or gain a lot of radiation from anything. Then it becomes adiabatic, and then for an adiabatic situation, there's a lapse rate, which is the rate at which temperature varies as a function of distance above the planet. And if you take a 65-kilometer thickness of the atmosphere, apply that lapse rate, and take the top of the atmosphere temperature of 220, you get 727 degrees Kelvin, which is very close to the measured value. So, anyway. It worked out, so that was pretty cool. And so now I understood this, and now maybe you understand a little bit, but it was kind of fun. Okay, so yeah, and of course, if Earth had an atmosphere similar to, and we didn't have plate tectonics and everything, we'd be in the same problem. We'd have the same problem that Venus has. Okay, so now we'll move on to what the climate change part of the talk. So how do we know that the climate is changing? And there's lots of things. One is ocean heat content, sea surface temperature, marine air temperature, sea ice, water vapor, air temperature, glacier volume, snow cover, temperature, sea level. Okay, so there's lots of data that's available to tell us what's going on. And here's some of it. And these what this is. I should say that most of the data that's will be shown on the talk from here on out is from what is called the IPCC 5, and some of the early ones. IPCC is the International Panel on Climate Change, and every 7 years they produce a new set of documents, and I'll show you This is 2 of 15 chapters of these documents right here. 15 chapters of this stuff gets generated every 7 years. The latest one was in 2013. And so this is data from that. And the actual data that's up here is, this is 4 data sets. So this is data, it's not a calculation. It's 4, and that's what the different colors are. There's 4 different sets of data. And so this is land surface temperature, and you can see, and here's by year, and up to 2000 and just beyond, 2013. And here you see, this is sea surface temperature, not quite as much of a rise, but it's still quite a significant rise. Marine air temperature, same thing. Here is sea level. Sea level has gone up. There it is in millimeters. It shows here about 50 millimeters of increase in sea level. And this is the summer sea ice extent, big time drop, something like 4 million square kilometers of sea ice has been lost since 1950. 4 million square kilometers. That's a lot. And it works out to be about 3.5 to 4% per decade. Okay, so this is data. Here's some more data. Actually, let me go back for a second. There's been a lot of discussion about this data, particularly the top curve here, because it looks like it's plateauing, that the temperature may not be increasing, and it's kind of flattening out. So it's noisy, but it does give that, so that's generated a lot of discussion. about that plateauing. Maybe it's over. Maybe, you know, it's not going to get any worse. Well, guess what? 5 more years happened since that data was produced. 5 more years. And this is what it looks like now. And this is the last 5 years right there. And so there's the plateau. And this is new data. You wouldn't have seen this if I'd given this talk a year ago. So this is, so I just got this last week. And if this plot here shows the temperature for each year over the course of the year. But so I've labeled each year. So you know you have this jumbled flat region in this period. But here's 2013, 14, 15, 16 was the warmest year ever, and then 17, which wasn't too far behind it. So you can see there's a very significant rise in surface temperature over the last 5 years, and that's what's responsible for this. So what is clear, at least to me and to a lot of people, is you see there have been bumps all along, and this is just another bump, in what unfortunately in an increasing trajectory up. And this shows something called the polar amplification. It's the fact that this is the temperature up in the northern latitudes from 23 north, essentially above the Tropic of Cancer or Capricorn, one or the other. Anyway, you see the large increase in here. Here is in the low latitudes, right in the tropics, and here is in the southern hemisphere. Less. And this shows the actual temperature on a global plot, showing the temperature anomalies. This is 2 degrees C, and the very reddest part of this. So some of the Arctic is actually warmed up that much. You don't have nearly the effect down here, except in one area, the Weddell Sea in Antarctica. And this is somewhat complicated, but it's actually fairly straightforward. This is the rate of change of temperature across the globe. And if you look at the scale here, this red here is about 0.8 degrees per decade C, 0.8 C degrees. This is 1. So you can see that up here, the rate of increase is very high, and it's getting close to 1 degree C per decade, whereas it's much lower in the as you go down. Yeah, I skipped over why that's all happening, but part of it is, I just go back here. It's in the words, and I didn't read the words. It's a reduction of snow cover, changes in the atmosphere and ocean circulation, presence of actually soot that's generated, anthropogenic soot in the Arctic that's causing it to warm up, and changes in the cloud cover. But all of that is rapidly heating the northern hemisphere. Okay, and so now we talk about ice. That's not a great story either. This upper graph is showing, so here you have cumulative ice mass loss in gigatons, and these are thousands, over the course of these years. And this is the loss due to glacier, and these are Greenland and Antarctica ice sheets loss. And it's quite significant. Greenland ice loss went from 34 gigatons a year in the 10 years between 92 and 2001, and up to 215 gigatons a year in the last decade. So, well, it's again, slightly old data, but it's big change. Almost not quite a factor of 10, but a factor of 8, 7. It's significant. And this is shown on these graphs here. This shows the reduction in ice on Greenland between 2003 and 2012. But if you break it down and you look at the 2003 to 2006, you can see there wasn't that much change. It's still changing, but look at the difference between 2006 and 2012. Huge changes occurred in just that last 6 years. Yeah, and not much is happening except at the Weddell Sea area in Antarctica. Okay, Yeah, and this is something that we're all familiar with, or most of us probably are. Those of us who went to Iceland, we saw it there. But what this is glacial terminus shrinkage. And the scale here, it's a little hard to read, but it's in thousands of meters, so that you can read it here. Here is a 2,000 meter line right here of loss. And this is Alaska, Western United States, Greenland, Iceland, 2,000, Svalbard, that's up in Arctic area of Norway and Scandinavia. So very, very, very large, significant decreases in glacial extent. Okay, so that's kind of a little bit of a picture of the data. And now we're going to switch to models. And I showed you some really simple models. Well, these things that are called Earth system climate models are not simple. They're very complicated, they're very sophisticated. There's 4 generations of this IPCC, and every generation has produced a more detailed model. You can see this is meant to show you the resolution is improved, but more importantly almost than the resolution is the effects that are being modeled. And in the previous one, the one that report that entered in 2007, IPCC 4, things that were modeled were things like atmospheric effects of convection, clouds, aerosol, boundary layer effects and radiation, land effects of vegetation, soil type, moisture, snow, temperature, feedback, ice sea effects of different albedos, reflection amounts for bare ice, melting ice, snow-covered ice, and open water. And then the 5th generation models include all of this, but they also include feedback processes associated with actually sources and sinks of CO2 and methane, aerosol particles and their interaction with clouds, and the radiative transfer process, and a more sophisticated model concerning ozone and its chemistry. So the models have gotten significantly more sophisticated, and now we're going to show you some results of the modeling. Okay, so here, now before I show you all the results, I want to just show you some of the effects that are modeled. This is more to give you a sense of the sophistication and the detail that these models go into. So the first is something that's included in the model, something called the cloud radiative effect. So this is the effect that the clouds have on the radiation. And I missed the point that I should have said earlier, and I'll say it right now. I'll say it, I'm going in the wrong direction, I'll say it now. I'm still going in the wrong direction. Okay. Many of the effects of the greenhouse gases and other factors such as clouds and aerosols are expressed in terms of a change in energy density in the atmosphere. This is called radiative forcing. And I mentioned that because a lot of what's coming up is going to be in terms of radiative forcing. And it's expressed in watts per meter squared. You know, the insolation from the sun was in watts per meter squared. Well, effects that change that radiation are called radiative forcing, and it's also in watts per meter squared. So as we go forward here, we'll be doing that. So here we have the clouds. This top plot is of the short wavelength radiation from the sun itself. And it has a major cooling effect. And the clouds absorb radiation from the sun, and you get minus 47 watts per meter squared of effect of less radiation because of the cloud intercepting the sun's radiation. However, just like I showed you in that simple model, the clouds now have gotten warmer because of that, so they radiate more heat down to the surface of the Earth. And so that results in a positive radiative forcing of 26.2 watts per meter squared. And then if you add the two up, the net effect of clouds, though, is cooling. It's a minus 21. Now these are just more detailed plots, but it shows you some of the sophistication in the modeling. This is the zonal average for the radiation directed from the sun, and the black is the data The red is an average of all the models. And in this case, and if you look carefully, you'll see these grayish lines. Those are individual models. So they're scattered among the model, but the average does a pretty good job. This is of the radiation that's getting from the clouds down, the long wave radiation again, and here's the sum of the two. Sum of the two isn't so great, but you know, it's not horrible either. You know, to me, it's still pretty amazing that they're doing this well. But this is an area which has the greatest, this cloud effect has the greatest disagreement between the various models that are used. In some cases, there's something between 50 and 100 models that are represented in most of the data that we'll be doing. And again, the red is an average of these models. It's called the, whatever. It's an average of all the models. Okay, so aerosol. Okay, so power of pollution. Pollution is actually helping us a little bit right now, believe it or not, because you get a normal cloud and the sun reflects off the cloud, it's fine. But if you now have pollution from the surface of the Earth, several things happen. One is that it makes the cloud tops brighter and it reflects more light. It also causes more water to nucleate because of the aerosol, and you get more water in the clouds, and as a result, less sunlight gets through. So the net effect, at least the net effect of aerosols, pollution, is that it has a cooling effect. And the model takes this into account. The latest model, this kind of interaction is included in the latest model. Okay, and this is the last of the new effects that I'm going to talk about. This is carbon cycle and sequestration. So the top plot here is ocean absorption, either sink or emission, and it's all in the sink side. So this is this dark black line is more or less data, and this is for the surface of the Earth, and again the black dark line is more or less data. The models are everything else, and the color of the model is the confidence. So in a 10% confidence level, that's what the model shows. But by the time you get out to a 90% confidence level and you look at all the models, you get the gray. But overall, you can see that the models are doing a pretty good job of predicting the shape of this of the ocean absorption of CO2. And not nearly as much absorption is occurring on the surface of on the land area, and that's also shown in the model results. Okay, and I went in the wrong direction again. Okay, so now we'll talk about the comparison of the model results against the data. And I'll switch back over here for a bit. So here we have a lot of spaghetti, and what that spaghetti is, all of this these fine lines all relate to individual models that are used throughout the world by the teams, and the red line here is the average model, is the average of them, and the black line is the data that we saw earlier, and you can see that roll-off effect here. And so if you compare the data to the model, and here's an overall projection. The data is by this red thing, and the model showed the spread in the model. So overall, the model actually has done a pretty good job of predicting the temperature rise, which is on the order of 1/10 of a degree C per decade on the average. But if you look at the details and you break it down, like 84 to 98, the model under-predicted the heating. You see, here's the temperature, and the models are all clumped here. And if you look at the last 10 or 15 years, up until 12 that is, the models are over-predicting the heating, which was right here. So that's kind of the story up until now. And this is the latest data that came from the IPCC. We'll have to wait until 2019 for the release of the next report. But I'm going to re-show this graph, this plot again. I showed it earlier. and I'll just make the point that yes, it did flatten, but it's the temperature is still going up very sharply, and it just says that the models aren't including all the effects that cause these some of these plateaus that periodically that seem to happen. But the overall effect of the rising is well reproduced in the models. Okay, and so this is again some more details of all of this. I'm again, I hope you're amazed by it, because I am. But this is the temperature. This is the calculation. This is strictly model calculation of the temperature on the surface of the Earth, and it's in degrees C, and the color indicates the temperature. And this is the precipitation, and the color indicates in millimeters per day what the precipitation is. So this is a model result. This is the comparison of the model result with data, and so this is the error. And so when it's yellow, it means that there's not much error. But you'll see there's a fairly large, the error grows in the tropics. Well, the error grows in the mainly in the Arctic and subarctic, Antarctic areas. Larger area here, also in the Himalayas, and that looks like Greenland. So there are areas of error there. But overall, it's I think darn good. This is the precipitation error, and the main error here is in the tropics, and there's a lot more rain than the models are showing. This is so it has modest improvement needed, but still pretty amazing. Okay, this is the sea level story, and this is interesting as well. So this goes all the way from 1900 to 2010, and this black line is the increase in sea level due to thermal expansion of the topmost part of the ocean. The dotted line includes measured loss of glaciers, and then the data is all the colored lines are data. You can see the individual models in gray, like has been shown before. And the red line is the change measured by satellite, and that's only recent data from 1995 on. So that's the satellite measurement. These are other measurements, and these are the calculations. Now, if you renormalize to 1960 and say set everything to zero there, and look at the changes from there, it's quite interesting. You'll see that the thermal effect, that is the warming, that the rising of the ocean due to the warming of the ocean strictly by itself, is the majority of the effect. And then there's an additional correction for the glaciers that are lost, and then finally this dotted line, which is newer, has to do with ice from ice plates, not from glaciers. And this is a small effect now, but it is growing. You can see that it's actually growing from the poles. Yeah. So the ice sheet contributions are small, but they're growing. Okay, and this shows a little more about the ice story. Again, and digging in more detail, this is the sea ice extent in the Arctic as a function of months. Black is data, red is the most recent data calculation, and the blue is the previous. And the bands of color have to do with the spread of the models. This is Antarctica. Not as good agreement, but you'll notice that the latest model is actually very close to the data. Model average is very close to the data. This is the extent of ice. This is the extent of the ice in the summer north, and the red line is the extent. And and then the gray area means that 42 of the models predicted it just like this. So there was 42 models involved with this calculation, and the fact that it's in gray, all of the models agreed. If you go down here to Antarctica, which is going to be in there, this is the Arctic winter, this is Antarctica at the same time, which makes it their summer. The agreement is very poor. You have only a few models actually agreeing with this, with the actual shape of the sea ice in their summer. But the agreement in the other two cases for the summer in the north and the winter in the south is pretty good, which again I think is amazing. Okay, one more effect that the models are showing is extremes. And so we'll start up here. On here we have cold nights, and so this is the exceedance rate in percent of cold nights. And as time is going on, we have fewer cold nights. And again, the red is the calculation, and the black is the data. And if you look at cold days, the same story goes on. Again, very good agreement. We have many fewer cold days. And we have, now if you flip the thing over, and warm nights, we have a lot more warm nights, again, and we have a lot more warm days. So extremes, one of the other effects of global warming are extremes. Now this is some data that literally I got off the radio, but I confirmed it just coming here. In 2000, in addition to the temperature extremes being wider extremes, there's going to be more extremes and adverse weather extremes. And in 2017 was one of the worst cases ever, we're all aware. There were 16 events costing over $1 billion each for a total of $360 billion of damage. Over the past, the average is 5 of these type of events. And yeah, this data is just coming out now because it's just now into the new year, and people are looking at the data, and it's pretty amazing.
Are those global numbers?
Global numbers, yeah, global numbers. Okay, so this is a little bit of a summary. It looks a little messy, but it's actually, I can explain it hopefully fairly simply. This top group, this is the radiative forcing between 1750 and 2011, again in watts per meter squared. And so this is what's called well-mixed gases. It includes CO2, methane, hydrocarbons, nitrous oxide. And so the biggest effect in radiative forcing over this time period is CO2. The next is actually, this is a little more complicated, it's worth spending a second on it. This part of this curve, this part of this curve right here, is methane. So that's a big, methane has a big radiative positive warming effect. But you notice this little light blue or green area, this is actually ozone in the troposphere. Ozone in the troposphere is a pollutant, and it's a greenhouse gas. So in the troposphere, ozone is a greenhouse gas. In the stratosphere, ozone is a cooling effect because it stops the shortwave radiation from the sun. But the net effect of ozone is it's actually warming. But the source of the ozone is different. This is pollution source, and the other is more of a natural source. But the models are accounting for the differences there. And then you have various hydrocarbons, and then you go down to the next group here, and this is short-lived gases, CO, NOx, and again, they don't have not as much of an effect, but NOx is a little bit of a pollutant, and it's a cooling effect. Then if you get down into the aerosols, and the pollutants, most of it is, as you can see, is cooling, with the exception of black carbon depositing on things like snow, which causes a net increase in radiative forcing. And then you get these other effects. The surface albedo of the Earth is actually, we're reflecting more light now. It's going up, and so it's actually the cooling effect because we've cleared more land. The reflection of cleared land versus non-cleared land is greater, so there's less heating. And then so the sun over this last period has gotten warmer too, so it's a small effect there. So in terms of the word anthropogenic means man-made radiative forcing since 1750. So you have 1950 0.57 watts per meter squared, 1980 1.25, and 2011 is 2.29. That's the integrate of all this stuff. And this is a complicated graph, but it's instructive, so I'm gonna walk ourselves through it. We'll start at the top and work down. The top is, so this again is effective radiative forcing as a function of time. Okay? And the little wiggles here, all that's sun, and that's 11-year solar sun cycle. The small black line underneath it is carbon on snow. The next line is actually water in the upper atmosphere. And then the next line is tropospheric ozone, and that's this big green area here. The next is other well-mixed greenhouse gases, and that's the light green. And then the big one down here is CO2. And then and on the negative side, you have the two aerosol effects. One having to do with clouds and the other having to do with the interaction of aerosols directly with the radiation. You have a land use, the albedo that I mentioned earlier, causing more reflection. And then the big, and there's a small effect due to ozone in the stratosphere, which is a cooling effect, but it's there, it's measurable, it has an effect. When you thin ozone, more of the radiation is going to come through, and that will diminish that. But that we, fortunately, man has dealt with that reasonably well. And the last is volcanic, and that's where these big spikes are. So these are separate volcanic. So when you add it all together, the black is the total of this, and the red is the man-made piece of it. So it's kind of interesting to see how it all goes together. Okay, let's see if I'm missing anything here. I don't think so. Yeah, okay. Yeah, I'm not going to talk about this in detail, just to point out the fact that these models produce a lot of different analysis all around the world for land surface temperatures, land and ocean heat content, ice extent, all over the world. Okay, and this is a comparison of models with measurements on a graphical standpoint. And on temperature, which is the top one here, this is 0.99. So this is very good agreement. And the difference between these generational changes in the models is mostly tightening of the model spread between the individual models. On precipitation, the agreement is not as good. 80 is more like in the 0.8% in the last. But notice how much tighter the model result is in this latest generation. So overall, pretty good record for the model. So now we're going to talk about the future. The way in which IPCC did this is they came up with 4 scenarios. And the 4 scenarios are these. The top one here is basically increasing, and is represented here. This is the top one. This is CO2, and it's basically taking what we're doing now and just continuing. And if we don't do anything, this is what's going to happen. This is the amount of CO2 concentration over time. And this is the total concentration. It's not the, well, this is in the atmosphere. It's the concentration of CO2 in the atmosphere. And then you come down into these various other models. And then this one is the one, and we'll talk some more about it. It's the only model that will actually show a decrease in the CO2 over time. And there's a similar set of curves here for methane and nitrous oxide. So these are the 4 models. Now we'll just walk us through some of this. The top graph here is sea surface temperature change. And there's only 2 of the models on the graph. This is the lowest model, the one which actually shows a rollover. It shows a modest flattening also. And by the way, notice the scale here. We're talking about 2000 to 2100 through this current century. But business as usual is going to cause a considerable amount of heating in the ocean. You'll notice, you remember what I said earlier, the heating is the biggest effect in terms of the amount of sea rise. 39 models, that's what this is. 39 models were used here, and 32 models were used here. And if you look at northern hemisphere September sea ice extent, this is no sea ice. And certainly these top couple of models, which are more or less business as usual and maybe a small effect, still, by 2050, there is no more northern sea ice if we don't do anything. The best most optimistic model is here, and the next one down here. But then, by the end of the century, the bottom two result in no sea ice. On the bottom here, this is acidification of the oceans, and all models except the one are going to cause a increased acidification of the ocean. This is not good for marine animals. Okay, and this is just changes in temperature and precipitation and ice. This is temperature. This is again now taking the model extremes. The best and the worst case, best and the worst. You'll notice this is pretty much obvious. This is more extremes in precipitation. You'll see the different colors amount to different changes, and you'll see much larger changes all across extremes of drought, more extremes of drought, more extremes of increased of increases as well. And the sea ice is all gone for this case, and it's still there in the northern hemisphere for the best case. Okay, this is an interesting story. It looks messy, but it's actually the story is fairly simple. This is the aerosol story. This is pollution. Well, guess what? The model assumes we're going to clean up the pollution, and that's great, right? But you see, right now, pollution is a cooling effect. But by 2030, they're projecting, even in the most optimistic model, it's actually going to have in North America and in Europe, it's going to have a heating effect because we've eliminated the cooling effect of the pollution. And all the way at the end, it's even more so. But if you look at the worst case model, and that's what you go down here, see there hasn't that much change. This goes from 0.09 watts per meter squared. But you see, now it's changed from negative to positive. So the effect of the aerosols is now, because the aerosols are disappeared, so it's a little weird, but they're not causing the heating, they're just gone. And as a result, there's more heating that's occurring. In the case of the worst case, this is 2030, and in the worst case, the aerosols were helping a lot, and when they were gone, it results in a much bigger change than in the best case. This is the sea rise, and the graph here only shows, I'll go back over here, the graph only shows two lines, but the intervening models are here as well. But here you see 0.4 of a meter for the best case, and 0.8 of a meter going up to a meter by the end of the century for the worst case. And what it says is that, so in terms of global mean sea rise for this period of 81 to 2100 relative to the previous, will be in the ranges of for 0.26 to half a meter for the best case, 0.32 for the next, 0.33, 0.63, and 0.82 meters for the worst case. And the other unfortunate thing is that that this is likely to continue. You see, these things aren't rolling over. They're just, it's still, all models are still going up. I'll show this for just one reason, because it gives a little more detail on this one graph over here. This shows, this is the sea level rise based on the various models that are listed down here. What's sort of interesting is the contribution. So this red is thermal, the next is glacier, the next is Greenland ice sheet, and this big one here is Antarctic ice sheet. And the reason the Antarctic ice sheet is vulnerable is actually, not much has happened, but it could have a huge effect, because there's a certain amount of let me talk about Greenland first. Studies show that a mean temperature rise between 2 and 4 would result in a near complete loss of the Greenland ice sheet over a millennium, 1,000 years, not in 100. And that will cause a sea level change of 7 meters if it all disappears. About 3.3 meters of equivalent ice in the West Antarctica sheet, which is actually grounded on bedrock and is vulnerable to instability. And that's what this big chunk is here that could happen if that actually disappears. And those are meters. But anyway, over the next 100 years, nothing quite so dramatic, but it's not good. It's not good by any means. And this just shows you a little, gives you some idea of what the impact is. Here's Florida. And the darker blue is elevations less than 5 meters. The lighter blue is less than 10 meters. So you can see 5 meters, 10 meters has big effects. This is even more depressing up in the northeast. All these outer islands are very low, and elevation of meters between less than 1 and from this dark green, and even going all the way in to the red, it's 5 meters high. So a multiple meter increase in sea level will cause big, unfortunate things. Now, just to put all of this in perspective, this is something that John Guslander put together when we were putting this together. He just looking at the sea rise change. The sea has changed a lot, and we're talking about meters here, but over the history, going all the way back, the sea has changed hundreds of meters in the past, going from greenhouse effects to icehouse effects, greenhouse effects to icehouse effects. Okay, we're almost done. This, literally, this this busy-looking chart here has a. This is the change in temperature over just the increase in average temperature, and this is the cumulative anthropogenic CO2 emissions since 1870, and basically it's almost a linear relationship. The more of this that happens, the more of this that happens. Now these various lines, the blue, all these triangles which end here, this is what happens up until 2050. And so it says that all the models are going to have some increase, but maybe no more than 2 degrees C by 2050. But as you get into the later years of, and by the way, I'm not just talking about 2100 here, we're talking about way out. Okay, so this is 2500 here. And so this is much further time. But, no, I'm scared, excuse me, this is, let me make a mistake. Total, this is just the CO2. Right, this is just CO2. And this is not time at all. But this is the end of the decade. This is the end of the decade projection for the worst case. And that gets you up into many degrees C. And the various other models come down here. Now, we talk about the 2 degrees C goal. With a probability of greater than 33%, the total carbon emissions has to be held to increase 900, they call these petagrams, these are gigatons of CO2. Okay, 900. You get, to hold this to 50% chance of probability, 820, and to a 60% chance, we have to hold it down to 790 gigatons of CO2. And this is cumulative. To give you a point of reference, 500 gigatons have already occurred. So to get a high probability, we have to keep it from rising much above 500, no more than 790. But what unfortunately it says is that there's probably going to be persistent warming with the exception of the one case beyond the end of the decade. And it's almost virtually certain that sea level will rise beyond 2100. You saw that earlier graph, and and most of it is due to thermal expansion, but the ice is going to have more of an effect on it. And the bottom line and point here that's made is that depending how soon you deal with these problems, they're a lot easier to deal with later on. And this is the last picture I'm going to show. It looks a little complicated, but this is what happens. This is gigatons of CO2 per year, and this is between now and 2030. And so this light green indicates everything above 55 gigatons per year, and the gray area here is anything below it. And these are the various possibilities ranging over this range that might happen. Okay, so if you look after 2000, so what this is, to maintain the 2 degrees C rise and have it no bigger than that, if we've done a good job, and this is the median of holding it into this area, if we've done a good job, we only have to decrease the amount of CO2 emissions by 3% a year for every year after 2030 and to 2050. And then, but if we haven't done as good a job, and we're up in this range, we have to reduce it from 2030 to 2050 by 6% a year to hold the 2 degrees. And this one is also interesting. Again, having done a good job, this has to do with share of zero and low carbon energy. So if we've done a good job, we need to use about almost 30% of low carbon or zero. And then in 2050, to again maintain that same 2 degrees, that has to jump up, so it's almost 60% has to be zero carbon. And then by the time you get to the end of the century, it's over 90%. Now, if you haven't done as good a job, it's not too painful by 2030, but by 2050, you have to do a huge increase in the use of zero carbon to make up for what's been happened. And in both cases, by the time you got to 2100, everything has to be carbon-free almost. So anyway, that's the challenge. And if you don't meet these challenges, the consequences are something more than 2 degrees, and worst case, above 5, 6, 7, 8 degrees. Okay, so that's the end. Leave the lights down just for a second. I want to show a few more pictures. I want to do a little advertising. This is my eclipse picture, and there's some. If you want to see them, there's a metal print of it over there. And here's another one of my eclipse pictures, and there's a metal print over there. And we have a huge. These things are available through Wyoming Stargazing's website, and I'm contributing anything you buy from them, they get it all. So profit. So if you want to buy any of these pictures, go to the Wyoming Stargazing website, and you can get these in paper or metal or almost any size. That's the largest size, the one over there. You can go over there and look for it later. And John, you'll have to bear with me. People were saying that the recent Iceland trip was very wet. You know, we had lots of bad weather. Well, we had some good weather too. And just show you some of the good weather pictures, and but also some of the interesting geology that we had. This is the mid-ocean rift above in Iceland. These are a basalt column formation. This is a leftover volcanic granite, actually gabbro, leftover volcanic basin. This is a big basalt field. This is one of the towns, and this is the Northern Lights. Okay, that's it. Yes. Oh yeah, I want to mention something about Thursday before you go. Now, if you want to get a preview of what will probably be a talk next year, is of the geology and scenery in New Zealand. I'm going to give that talk at the Rec Center on Thursday at 6:30. So that'll have geology in it. We'll also have lots of pretty pictures. Okay. Yeah. Mary. Okay.
The chart that shows the spike in temperature.
Yeah.
That goes back to 1890.
Yeah.
Do you have one that goes back 10,000 years?
Yeah, because the ones that show the ice core data do that. You know, yeah, I don't have it here, but yeah, that does exist through ice core data and other things. Yeah.
So is that temperature the highest ever?
Oh, I see. I don't think so. I don't think so. Someone probably, no, we've actually seen higher temperatures in the past than we're dealing with now, in the deep past of Earth's history. Bob?
And Mike, comment a couple of questions if you give me a minute here.
Yeah.
Comment. You and I and half a dozen other people in the case of beer could sit down and talk about this stuff ad infinitum.
Right.
There's a lot of every other graph raised a question. Question number one. You show the solar insolence averaged over the entire projected area of the Earth at 200 and some odd watts. Okay, so, but the insolence at equatorial regions versus polar regions is vastly different. That stirs the weather.
Yeah.
Right? Now, the other question is, you showed sea level rise based on, and you had to label the other red line altimeter.
Where?
And then you said satellite.
Yeah.
What was the satellite mechanism?
It's an altimeter measurement. Now the question is, what was the measure? What was it? I don't remember how that measurement was done.
You're measuring, I think, up to about a 20 centimeter or something like that sea level rise. And I have a question as to how accurate you can determine the altitude from a satellite.
Yeah. And I don't know the
I
answer
think
to
the error
that.
bar in that.
But you'll notice that the other data, the other colored wiggle lines,
Yeah.
were other sources of data.
Your graphs were very much full of colored wiggle.
Yeah, well, they're not my graphs.
I understand.
Yeah, these are graphs. And by the way, if you want, all of this stuff is available to everybody. I mean, if you want to dig into it, go into the IPCC, and you can look at all of these graphs, and it's all available. Okay. Anybody else?
I'll stop at that point.
Yeah.
Hi. I have a question. I don't know if you can explain it. I live here half the time, so half the time I go back to Texas.
Yeah.
And I'm constantly getting feedback that there are a lot of prominent meteorologists that are disagreeing with the, I guess I'm not familiar with the word anthropological.
Anthropogenic.
That it's man-made. Can you discuss where the contradictory opinions are criticizing
Yeah, and
the
to be
data
honest,
you're putting up there?
yeah, I've had a certain class of contradictions that I've been trying to deal with, but as far as that class, which is, are you thinking about the projections looking forward, or just where we are right now?
Well, looking forward.
Looking forward.
Yeah, but I think most people realize that there is a change and that we're getting warmer. Now,
But you
all
can look,
these-
but you see the measured changes occurred already, and that's there.
Right.
It's happened, and it's very well correlated with the amount of pollutants, CO2, that have been eaten. So the projections looking forward, yeah, it's a projection. But on the other hand, what the models do is just say, all right, if we just take this line and continue it on and assume that that we're going to not be able to do anything about it. In fact, humans will create more CO2. And that's where those other models are. Now, but all that's up to grabs. I mean, if we can somehow get our act together and do something about it, the story changes. If we can somehow get all the way down to actually putting a cap on it, so that the actual amount of CO2 decreases, that would be very difficult, but it would then keep us in this 2-degree range, and life would continue pretty much like it is right now, without a lot of change. But we're not on a really smooth path right now to get there.
Wasn't the tipping point the industrial revolution?
Yeah, well, that's stuff.
That why you say benzoogenic?
Well, that's why it starts there, because that's where the anthropogenic pollution first really happened in any measurable amount, was the industrial revolution. But we've added to it much more significantly in the last 50 years or 60 years. Yeah.
Mike, what's the ideal temperature for the Earth?
What do you like? Well, right now, it's 14 degrees C.
Okay, that's what it is now. Is that the ideal temperature?
Well, as you go up in temperature, as I was mentioning, several things, as the Earth warms, things happen, and extremes happen, more extremes happen. And because the projection, just look at what's happened last year in terms of the weather. That's the type of thing that the meteorologists and others are saying are going to happen as we go forward. Because it's not just an increase in temperature, it's an increase in temperature range and in extremes. So the more energy, and it all comes down to the more energy you add to the atmosphere, and the more likely bad things are going to happen. So that's the problem.
Yeah, so there really is no answer.
Well, lower is better is the answer.
Lower?
Actually, warmer is
Tell the
better.
people back east right now that that's the answer.
Well, okay, well, and even, what's the interesting things about the extremes is that even in a warming climate, there are going to be colder extremes. And the fact, look at, the extremes are going to increase. Cold and hot. Yeah.
Well, the other thing is, even if it's more comfortable and we don't have to wear coats and everything, it's not going to be a very good life if half of the biological species on Earth are extinct because it's changing so
Yeah,
rapidly.
and the oceans are getting, the life in the ocean is going to be marine animals because of the heat in the ocean, acidification in the ocean, oxygen lack of oxygen in the ocean is causing bleaching of the, and so lots of bad effects occur to life other than us.
Mike, our videographer's trying to get
Oh,
started.
Two comments. One of the, it depends, it's all relative. If you're a dinosaur, you might like a little warmer. The issue is what is a range that humans, because that's our interest, could thrive in. That's the question. But if you're another species, maybe you'll like it a little warmer or a little colder. That's the answer to that. And I heard two other things. Once I overheard somebody talking at the gas station who's a rancher, I guess, had family in Idaho, and he said the calves over there were calving, the cattle were calving. And he was saying it was like 2 months early. So I can't prove that or disprove it, but people who are paying attention to animals in this group, pay attention to the animals and how they may be changing their rhythms relative to our weather that we've been having anyway. And the other thing is a question for you. How is population variable in all of this? Because if we double, is that taken into consideration, or are we just talking about who's here now, or what?
Yeah, I don't think population has been directly mentioned here or included here, but some of the projections, particularly the higher projections, are more likely with a higher population. So that would be one of the challenges. It's not just that our existing population has to keep its act together. It's the fact that the existing population is most likely going to increase substantially, and that's going to make keeping these much more difficult, because that means the pollution per person has to go way down. Yeah. That's a good point, of course. Yeah.
We had a comment and question about CO2 emissions into the far future, and I think your graphs went centuries into the future looking at CO2 reduction. Isn't CO2 emission into the atmosphere a self-limiting situation, considering we have a finite quantity of carbon-bearing fuels that we can burn? We're going to run out of them. I don't know if it's going to be this next decade or the next century, but we're going to run out of them.
At some point.
Yeah. So
that's the good news.
Do the projections take that into account?
No, because no, I'm sure they don't. I'm sure they don't. But I don't. I think in any of these graphs, they actually ended. I think we were only talking about this century.
Some of them.
Yeah.
I can
Yeah.
comment on that.
Okay.
You can see the maximum by looking at the past. And so, in the past, the highest the temperatures have gotten, say, 10 degrees centigrade warmer than they are now. You know, because we have good temperature records for 500 million years. The other thing I want to comment on that population one is one of the leaders of that international panel of climate change, the one that got fired. But he was asked that question and he said he wasn't allowed to consider it. You know, all these people are employed by governments and they would get fired if they considered
Tell the truth?
population. Well, you can't talk about population and keep your job if you work for the government.
So we have time for 2 more questions.
If I could just ask, I thought you showed a really interesting graph, and that was the sea level that's gone over time period. So if there were times when the sea was high, well, let's say maybe not go back much more than 2,000 years or so, how did it correct itself?
Yeah, well, it's because we've gone through some very extreme changes with, with cooling effects having to do with, once glaciers form, the sea level, drops significantly. But then when we get through the ice age and it warms up, so it's the period of glaciation and warming between the glaciation that's caused that huge change. Because during periods of when the Earth is largely frozen, there's much less water in the ocean than there is when it's. And clearly, when it all melts, that's where it goes. And you can see the projections. If we melt what's in Greenland, 7 meters, and if we melt what's in Antarctica, forget about it. Yes.
At the beginning, you were talking about plate tectonics.
Oh, yeah.
The importance of it. How does that tie in?
It didn't, except in the early discussion about the difference between Venus and Earth. And it's like Venus does not have, Venus lost its water. Water is a key part of the lubrication that causes plates to move. Okay, Venus lost its water, and so there was no sequestration of CO2 in the planet itself. It's all in the atmosphere. We didn't lose our water. We still have it. Plates are moving. Water is storing CO2. A lot of the CO2 is in the oceans also. Plus, it's stored in the crust. But plate tectonics is, the lack of it causes everything to be up in the air.
Yeah, so it's the usual chair drill. So these chairs go this way, these chairs go this way. Please join me in thanking Mike for